let's try this again. Okay, welcome to my office. So today I'm going to try and go through the slides, not like go full force. Just just check about timing. Okay, and I can't tell. Okay, I can tell in there. Okay, so it's like 8:50 now. I'm going to go till 9:10. Okay. First, I'm just screen recording the slides over here so that I can make it into one video. Okay. Of course, like now, like. Why do they always move stuff around? I know it's like half me. Okay, so I think this is gonna work. I would like it to look a little different, but let's see. I just wish it was like slightly different. Oh, here we go. This is a little better. Okay, this is okay. We're just gonna do it like this. Just timing. Okay. Welcome to my talk. It's Chicago. Isn't Chicago amazing? Isn't Chicago beautiful? So nice. Such nice weather. Mitchell break for super compactness. So this talk is, I would say, very mathematical, but because of the nature of large cardinals enforcing, we're like in the independent realm. So this is actually very philosophical also. And I'm very happy to be here. And thank you so much for letting me talk here. We're going to be talking about supercompact cardinals. So the idea that we're going to be talking about degrees of supercompact cardinals. And the degrees of measurable cardinals are already defined. And so we're going to talk about a few large cardinals in this talk. One of the large cardinals is measurable cardinals. And they're similar to supercompact cardinals. And like the ideas of the degrees is really similar. And the ideas of the proofs well, I'll tell you about the softly killing them thing in a second. The ideas of the proofs are very similar. So this is a cardinal cardinal kappa is measurable if it's the critical point of a non-trivial elementary embedding J from V to M with M in transitive class. So this kappa is the first point moved by J. He says, I fly above the rest. I start trends. Okay, so we have an ultra power embedding, critical point kappa, and okay. So there's lots of definitions of measurable, and here's some other favorites. An unnumberable countable cardinal kappa is measurable if there exists a kappa complete non-principal ultrafilter. And so here in the picture, we're coloring the subsets of kappa either big or small. And so it's an ultrafilter, so any set is going to be called either big or small. And if it's small, if you're small, then your complement is big, and if you're big, your complement is small, and that's what the ultrafilter part. So we can measure the subset of kappa where the intersection of less than kappa many big sets is still big. That's the kappa complete part. Okay, and so we have these two definitions. An uncountable cardinal kappa is measurable if it's the critical point of a non-trivial elementary embedding J from V to N, or definition 2, there's a kappa complete non-principal ultrafilter on kappa. And for the idea of how these definitions are equivalent, if we start with a kappa is the critical point of an elementary embedding, then use the set of all U would be the set of all X subset of kappa such that kappa is in J of X. If kappa is in J of X, then we're going to say X is big. If kappa is not in J of X, we're going to say X is small. And so this actually creates a kappa complete non-principal ultrafilter on kappa. And we go the other way, we have this guy that he's painting all the subsets of kappa big or small, like purple or blue. So if we have this, if there's a kappa complete non-principal ultrafilter on kappa, then the ultra power by that measure, it does create an elementary embedding with critical point kappa. And so in V, again we see the guy. He says, "Oh my fly, I love the colors." He loves all the colors that guy painted. If anyone's like, oh, let's talk about ultra power embeddings again. What are those again? Or like, aren't those interesting to talk about? Okay, this is a short ad break for my book, The Set Theory Guide for Artists. It's chapter 3 is finished. Chapter 4 is in the works. There's going to be 7 chapters, and it's by the end of it really is actually this topic of forcing in large cardinals and how forcing to softly kill the degrees of large cardinals. Okay, so we can just look at this real quick. This nice picture. So the idea of we're in the universe, and we have an elementary embedding well, what is an elementary embedding? Just that like truth passes through E in this case, or through J from the models. So you have this ultra power embedding. You form this ultra power. And then everything's like a little weird, and we use like Scott's trick, and then everything's like a little weird. Where are we? We're not in a transitive place, and then we take the Mostovsky collapse, and then we're back in sort of a transitive place again. And okay, so we have this commutative diagram. You take the ultra power embedding and take the Mostovsky collapse. So J is the composition of those two. Okay, and you can read it more. That whole chapter is about that section of that chapter is about the producers of the universe, and they're going to make a new universe, and they have some budget constraints and stuff like that, and they're making this ultra power embedding, and it's like the birth of the measurable cardinal. Okay, so other large cardinals that might make an appearance, they might only be on this slide, I don't know, but strongly compact cardinals, they show, there's a lot of theorems about strongly compact and supercompact cardinals. I don't know if they're going to be included here. Inaccessible cardinals and malo cardinals, we can talk about the degrees of those because they're in my thesis, in this paper, I defined like the degrees of inaccessible and malo, and those are really interesting. And also we have like Ramsey cardinals. I just want to show Ramsey there with the colors. I like Ramsey cardinals. And ineffable cardinals. And then all the other large cardinals, like what about us? Because they all kind of fit together, and they're all friends with each other, and they're all kind of connected. Okay, so the bigger idea, so we've got the large cardinals, and then the bigger idea is we have these large cardinals, we have these degrees of large cardinals. We'll talk about that in a second. But before we even get to the degrees of large cardinals, this idea of like softly killing between different large cardinal notions has been all over the place, and it's like a theme of set theory. So Schenker, for example, has this theorem: if kappa is weakly measurable, and the measurability of kappa can be destroyed while preserving the weakly measurable parts. So it's always like destruction, but then like preservation. Kappa is strongly Ramsey. There's a forcing extension where kappa is not weakly measurable, but it's still strongly Ramsey. If kappa is strongly Ramsey and ineffable, there's forcing extension where it's not ineffable, but it's still strongly Ramsey. And this is interesting. So we're talking about degrees of supercompact cardinals. There already are kind of degrees of supercompact cardinals, and that's like your level of supercompactness. And so this is saying you can go to a universe. You're theta supercompact. You can go to a universe where you're not theta plus supercompact, but just theta supercompact. There's already this division, but now within this, you can be theta supercompact and then have a Mitchell rank for supercompactness 3 or 4. So even within the levels of supercompactness, there's more levels within those, and that's what this talks about, and also killing them. Okay, and then also like Magador, you can separate strongly compact and supercompact. Okay, and these are strongly compact and supercompact are real tight. Okay. So the inevitable degrees of large cardinals, and this is a philosophy song, so I say the inevitable degrees of large cardinals, because it sort of just seems like they're just sitting there and they want to be there and like they're coming up. Okay, so between inaccessible and malo, there's lots of space, and so this is showing the first one is just an inaccessible cardinal. It's regular strong limit cardinal, and then what if you took a limit of inaccessibles? That's one inaccessible. What if each of those inaccessibles was a limit of inaccessibles? Well, then you'd be 2 inaccessible. And what if each of those limits was a limit of inaccessibles? You get 3. And you get these nice pictures, sort of like fractally type thing. Okay, so the degrees of large cardinals. So, for example, kappa, these are degrees, the inaccessible degrees. And this is very interesting and could be its own talk. And it's just like you can use, because if you're let's say your kappa is 1 inaccessible, 2 inaccessible, and we can go up to kappa inaccessible, and that's called hyper inaccessible. But you can't be kappa plus 1 inaccessible, because you can't be like a limit of kappa inaccessible cardinals, because you are kappa. So then we have to, that's why we relativize with this omega big OR symbol. And so you say you're hyper inaccessible, you say you're ORed inaccessible, or I guess you could say you're ORed inaccessible. And then there's all these levels like that where you can't go in this direction, you can't get bigger in this direction, you have to kind of relativize. Okay, so we have different degrees. ORed inaccessible, hyper inaccessible, richly inaccessible, and then words to go with them, because what am I saying? ORed squared plus ORed. And then you have this basically Cantor's normal form, but for degrees of large cardinals using ORed instead of big ORed instead of little ORed. Yeah, it sounds cool. It is cool. Malo cardinals and their degrees. Malo cardinals also have a very similar large cardinal. Malo cardinals and degrees of them came first, and this is sort of inspired. Like, oh, let's define carefully the degrees of inaccessible cardinals. Okay, so Malo cardinals, we have the similar idea, and Malo cardinals, I say like Malo cardinals love inaccessible cardinals. Cardinal Kappa is Malo if it's inaccessible, and instead of inaccessible below it, form a stationary set. And so your one Malo, instead of being like a limit of Malos, the Malos are stationary, and you sort of reflects back to the original definition. The degrees match the definition. Okay, and then the idea is we're going to kill them softly. With Malo cardinals, it's kind of straightforward, and I think this has really been around since the beginning of Malo, like in the 70s. How do you kill Malo cardinal? You add a club of non-inaccessibles. If you have a club of non-inaccessibles, then the inaccessibles are no longer stationary in the Malo cardinal. It sounds like a joke or something because it's a quick punchline, because it's a quick answer. So and we can do it for any degree, any T Malo degree where T is a meta-ordinal, having parameters less than kappa. That's the idea with the parameters less than kappa. It shows you those roadblocks. You can't have like in your presentation kappa show up for your degrees of kappa. Okay. Now there's also this. We can also softly kill inaccessible cardinals. If kappa is alpha inaccessible, there's a unit forcing extension where kappa is still alpha inaccessible, but not alpha plus 1 inaccessible. So the first step is force the GCH if needed. We can do this a lot, and we're going to do it because it helps do the math, and also we're going to do like Easton forcing, I think in this one, to like control the continuum. So it's good to have the GCH. We can always force that. It doesn't mess with the large cardinals. Okay, there's a forcing. I do not create nor destroy inaccessible cardinals. Did I say what the forcing is? I think I'm going to. But this is so we're going to force. So this forcing is we're going to see what it is. Oh, it's just the forcing to create the GCH. I'm sorry, I forgot my own picture. Yeah, that picture, that blue is just showing the nice GCH pattern. Okay, I was like, what is it doing? Okay, that's what P is. Okay, and then C is going to come along, and C is going to C preserves cardinals and cofinalities and strong limits, and adds a club with no alpha inaccessibles, but has unboundedly many beta inaccessibles for beta less than alpha. So this process, we're going to cut it down to just level alpha. And seeing that it has unboundedly many beta inaccessibles for beta less than alpha, that's going to help make sure that it still stays. You don't want to like kill everything, right? Okay, so we do that forcing, and then finally we do the forcing. This forcing destroys strong limits that are not limit points of this new club that I added, and so it will so that's where we're going to get that lowering of the degrees. Preserves all cardinals and cofinalities. Okay, this stuff's all really interesting. Okay. So, theorem, the big theorem, if kappa is alpha inaccessible, there's forcing extension where kappa is still alpha inaccessible, but not alpha plus 1 inaccessible. This guy is like, did I destroy too much? No, everything's fine. We forced the GCH, we forced to add this club, and then we did the Easton forcing, and we're good. And in the end, kappa is alpha inaccessible, but it's not alpha plus 1 inaccessible. Okay, so degrees of measurable cardinals. This is measurable cardinals. I'm not just measurable cardinal. I'm a rank 2 measurable cardinal. So if you notice, he has these little rankings on his shoulder. He's a rank 2 measurable cardinal. So what does that mean? If a measurable cardinal has a Mitchell rank at least 1, it's measurable. If it has Mitchell rank 2, then it's not only measurable in V, but in M, kappa is also measurable. So that's notation 2. That's the notation is order of kappa is 2, and he's also. There's the Mitchell rank comes from the Mitchell order on the measures on kappa. So you can order the measures being like, oh well, are you if mu is less than nu if nu is in the ultra power by mu. Okay, and then we can define the order of kappa is the sup of the orders plus 1, where mu is a measure on kappa. Okay, and this is just another way to say this is a really nice way to say it. The order of kappa is greater than or equal to 2 if and only if there exists a mu which concentrates on measurable cardinals. And it's rank 3 if there's a mu which concentrates on rank 1 measurable cardinals. So concentrating on means you're in the measure. If kappa, you're big. If kappa is a measurable cardinal, then there's a forcing extension where order of kappa is 1. The forcing will preserve all measurable cardinals and not create any new measurable cardinals. Can forcing create large cardinals? Yes, it can. But we have Hampkin's paper extensions with the approximation cover properties have no large cardinals. Okay, I'm seeing my time kind of running out. So, okay, so we want to do something where a lot of times we want to preserve the degree along the way, but we do want to kill it a little bit. Okay, so the big idea for softly killing measurable cardinals is we started in the ground model and we want to lift this embedding. So we need the diagonalization criterion, which gives us like a filter that we need, especially like on the tail, and the lifting criterion actually asks us to lift. Okay, and this is all a lot of Hampkin's work. So this is the diagonalization criterion, lifting criterion. So this is just the measurable case where if kappa is measurable cardinal, there's a forcing extension where order of kappa is 1. So you'll just be measurable. You won't have any higher rankings. Okay. So we are going to add a club of non-measurables at inaccessible stages, and then we have to lift. And the other part is we have to lift through the rest of so J of P factors. So P and J of P agree up to level kappa, and so we can factor J of P as P star Q dot, which is like the kappa stage star P tail. So we have to lift through all those other pieces as well. And so in the end, we do end up, you can see in the picture, he is a measurable cardinal. He's just got the rank 1 though. He doesn't have any higher rank, okay, which is what we wanted. Okay, so I'm trying to get to the main, okay, so they have these other more general theorems. You can change your Mitchell rank to whatever you want. You just can't go above what you already were with this forcing. Okay, so the leading rule number 2 is supercompact cardinals. And supercompact cardinals look a lot like measurable cardinals. A cardinal kappa is theta supercompact. It's the critical point of an elementary embedding J from V to M and M theta subset at M, where theta is between kappa and J of kappa. So that's why he's got the glasses on, because M can see a little bit. M can see theta sequences. And since I fly above the rest, I start trends and I can see. Okay. And kappa is supercompact if it's theta supercompact for every theta. And so what does rank 2 mean? Rank 2 means he's a rank 2. He's got the rank 2 on. We're going to fix theta, and it just means that he's theta supercompact in M as well, just like with the measurable case. Okay, just like the measurable case, you can read these definitions. So the order of kappa is 3, is J from V to M. He's measurable in V. I mean, theta supercompact in V. And then this guy says, I'm theta supercompact in M too. And this guy says, I'm theta supercompact in M prime as well. So that's order kappa rank 3. And we can see in the end, that little guy that's theta supercompact in M prime to M double prime, he's just got the rank 1. So he's not higher rank. So that's a solid rank 3. We've got 2 minutes. Okay. The Mitchell order for normal fine measures. This is just going back to, this notation is built off this ranking on the measures themselves. So this is the final definition, and yeah, you have this subscript. You can leave space for it, and that's fine. And we can get into the collection of normal fine measures on P kappa theta. So I was going to draw a picture for normal and fine. Normal means you're closed under diagonal intersection. This is diagonal intersection. Gamma is in the diagonal intersection. If it's in all the sets up to that level index. And then fine measures, they eat these kind of flowery type things. Okay, I don't have time to go into it. Okay, so I have these lemmas. I'm going to these are very helpful lemmas, especially lemma 1, but I think I ran out of time, so maybe I should just keep, okay. So I'm going to have to go a little quicker in the beginning. Okay, we can skip over some of this stuff. I just want to get to the story. Okay, softly killing degrees of supercompact cardinals, the final boss. So the idea is that in the forcing extension, you can have any degree of we use these representing functions, so it keeps it completely general, and we'll see this in the story. Okay, so let's see the story. We begin in a world of math, a nice place, quiet in the night while the mathematicians and large cardinals sleep. No drama for now, just a couple of functions on ORD. They're kind of classes, so they're creeping out. If you've already seen this, okay. Rising from the ground is a force of nature. It eats and support ORD length iteration. He adds gamma add a club such that C gamma is subset of gamma. Okay, and these would be at inaccessible stages. Then along came a fairy from somewhere else. Let G subset P be V generic. We zoom into the first inaccessible. Mathematicians observe P has a closure point, so it satisfies approximation and cover. And so this word soon spreads that P does not increase Mitchell rank for theta supercompact. Did you hear it? What's going on? But there were not any other large cardinals in sight yet. We meet kappa, a big theta kappa supercompact cardinal such that they have these properties. Okay, we're trying to keep it really general for the theorem, but I like to think of it as this user likes to keep an air of mystery about them. So the kappa looks in the mirror and is wondering, am I still gonna have this theta and F still representing me in the forcing extension so I can keep this theorem really general? And we see the mathematicians use that V satisfies the cover approximation and cover properties, and we also see that they're writing down this induction proof, and that's how the proof goes. And we pick a J where kappa has a low rank in M. We can do that with the lemma. With the help of the mathematicians, we successfully lift J to V of G with a lot of details in there. And kappa looks around the new world. Did I destroy too much? Not enough? Am I still me? The mathematicians assure us that because of the lift, beta arbitrary, and because of induction, blah, blah, blah. Okay, so yes, the Mitchell rank went to specifically what he wanted. We don't know why exactly he's going through this, but now maybe he's meeting someone there. I don't know. So here we go. We have the order of kappas exactly as we wanted. Okay. And then my references. Okay. And then if someone says, where do we use GCH? Okay, that's it. Thanks, guys. Thanks for coming to my talk. Okay. So happy to be here. Okay, guys, thanks for listening. Okay, I'm going to go screen record, stop record. Stop recording. Stop broadcast. Okay, guys. Thank you so much. Okay, thank you so much for listening. I'm going to write. I have to work on writing the paper because I want to submit the paper, which I should have submitted 10 years ago. I'm going to submit the paper. I want to submit the paper before the talk, or maybe during the talk, but very soon. And then after that, I want to work on the next paper. And then there's also some other stuff I want to work on, like abiding cardinals. Okay, so I'm going to share that with you guys as we go along. Thanks for watching my other videos and listening to that prime stuff. I might have gotten a little carried away at the end, but a lot of people watch that video. So thanks so much for watching. And if I might see you in Chicago, hopefully I'm going to see some of you in Chicago.